To lesson 4, dispersion and total internal reflection. Okay, so one of the interesting things about light is that it slows down when it goes from one material to another, and this causes it to refract or bend. So if I turn on the laser beam, the light shines, it hits the water right here. So this is air and this is water. And the angle of incidence in this case is 51.9, and the angle of refraction is 36.2. So it bends towards the normal. So the interesting thing is that how much light bends actually depends really slightly on its color. So in this advanced simulator, I can see that the red light is refracting at 45.8 degrees, but if I change the color of the light, the angle of refraction changes. So if I use violet light out of a laser beam with the exact same angle of incidence, the refracted angle is 45.2, and then if I make the light red, it goes all the way to 45.8. Okay, that's a difference of 0.6 degrees. It is not big, it's a small effect, but it's important. So the idea is that when light refracts, how much it gets bent depends on the index of refraction, and the index of refraction varies very slightly by color. So here's a graph that kind of shows the index of refraction for an ordinary glass. So for violet light, ordinary glass's index of refraction is about 1.53. But for red light, the index of refraction is about 1.51. So it's not a huge difference, 1.53 to 1.51, but it is different. And what that means is that violet light bends slightly different amount than red light. Violet light bends a little more than red light does because the index of refraction is slightly higher. And this has to do with that whole electronic levels of the atoms slurping up the wave and then burping it along to the next atom. And as it goes through there, the speed at which it goes from one atom to the next depends very slightly on its frequency. So the end result is that the frequency of the light has a small effect on the index of refraction, how much light slows down. So what that means is that if you take light, like white light, and you pass it through a media that causes it to refract, the red light will bend a little less than the purple light or the violet light. And so here's an example of refraction happening twice. Light passes into the prism, and red light bends a little less than purple. And then as it passes out of the prism, it bends again. And so this causes what we call angular dispersion. So dispersion is the separating of the colors due to the slightly different angles of refraction. All right? So each color refracts at a slightly different angle, and dispersion is the effect that produces this rainbow, this familiar color spectrum that we associate with the prism. Maybe your grandma's got some light catchers hanging in her window, so when the sunshine hits them, they throw little rainbows across the room. That's refraction and dispersion. So refraction is the bending of light, and dispersion is the spreading out of each color because the refraction is slightly different for the different colors. So here's an example of a picture that I actually took in Glacier National Park, and it was a double rainbow. And so this is an example of dispersion, refraction, and reflection. Let's look. Here's what happens with a raindrop. A raindrop is roughly circular when it's suspended in the air, or even if it's falling. And light comes, and this light consists of all the colors. It's white light from the sun. And when it hits the raindrop, most of that light is refracted into the raindrop, and that causes it to start spreading out. Now, when it gets to this interface right here, most of the light, and that's not shown here, most of the light is refracted again and leaves. It keeps going this way so that people down here on the ground will still see the sun shining. Okay? But some of it, not a whole lot, some of that light is actually reflected inside the raindrop, and it continues to travel across the raindrop. When it reaches the other interface, it's refracted as it leaves. And so light coming in from this direction can be sent back in this direction, but the colors are slightly spread out. Okay, now how that makes a rainbow is like this. The sun has to be behind your head, so the sun is over your head shining. Some sunlight hits a raindrop, and the red light is refracted at an angle like this, and that red light goes straight to your eye. But the violet light and the other colors are bent slightly more, and they end up going over your head. So in this region of the sky, you see a very faint red glow. Down lower, however, the red light is not bent very much, and it probably hits your toes. But the violet light is bent just the right amount to reach your eye, and so in the lower region of the sky, a little lower there, you see violet light. And so you see all the colors from red all the way to violet faintly glowing in the sky from these water droplets, and that's the rainbow. So when you look at a rainbow again, you can check and see the color on the top is always red, the color on the bottom is always violet. Let's just go back there and take a peek. So you can see the red is on the top and the violet is on the bottom, and it's very faint. It's not a bright effect. Now, some of this light which hits here also is reflected and goes around here, and it goes around here, and it goes out again. And that's what causes the even fainter second rainbow. So that's just more reflections and refractions inside as the light bounces around inside the water droplet. But that's what we call dispersion, the spreading out of light. Now, there's another effect we're going to look at called total internal reflection, and I solved a problem here which I'm going to skip. What I want to do is just talk about internal reflection here. So let's go back to our simulator now, and right now the laser beam is in air, and the light beam is traveling into water. I'm going to switch that. So let's make this water, and let's make this air. So imagine you're in your aquarium, and you're shining a laser beam from the water to the air. So here's what happens. When the laser beam hits the interface between the water and the air, it gets bent. But because it moves faster in the air, it gets bent away from the normal. So you can see this is 42 degrees. A small amount of light is reflected inside the water tank, but most of it travels outside at 63 degrees, so it's being bent away from the normal. If I move this, you'll notice the angle of incidence is getting bigger, but so is the angle of refraction, and there's some point here where it just disappears. So right here, this is 48.6 degrees. We're getting very near the critical angle. If I make it any bigger than 48.6, this angle here gets bigger than 90, and the light just internally reflects. So let me go back here and just do a little experiment. This is an intensity meter. It measures how intense the light is. So right here we have 100% of the light beam, and it's getting refracted, and 43% is getting refracted, and 56% is getting reflected. So more than half the light is bouncing right now. But if I go past the critical angle, no light is refracted. All of the light, 100% of the light, is reflected. This is called total internal reflection. So light, when it is traveling in an area where it moves slow and it's going into an area where it moves fast, light has a critical angle. If you shine it straight down, it passes right through. But if you start shining at an angle, the refracted angle is bigger than the incident angle, and at the critical angle, all of the light is totally internally reflected. Okay? We call that total internal reflection. That only happens when light is going from an area where it moves slow to an area where it moves fast. So when a ray of light is going from a slower medium to a faster medium, there's a special angle called the critical angle, and that's the angle at which the refracted rays are 90 degrees, or right along the surface of the interface. If the incident ray is greater than that critical angle, the light is totally internally reflected. Okay, sometimes called TIR. And this is the principle behind fiber optic cables. So with a fiber optic cable, you have light traveling in a pipe. It's usually plastic or something that is clear, and it's got some kind of cladding out here where light actually travels faster than it does in here, and that causes internal reflection. And so you can send a beam of light in here, and that beam of light just stays inside the pipe. It just bounces around all the way over, and no light is lost at all. None of it leaks out. And so this is what we call fiber optic cable, and we can make these cables and we can lay them all the way from New York to England, and we can send light through them, and we can use the light to communicate signals. Nowadays we use the light to communicate digital signals by turning the light off and on really fast. And even in Hancock County here, we now have some people who are connected to the internet via fiber optic cable. So fiber optic cables use internal reflection to keep all of the light inside as it travels through the pipe. And even if the pipe bends and twists a little bit, it doesn't matter. The light stays inside of it. That's called total internal reflection. Another example is the diamond. So one of the things that is special about a diamond is that it's very brilliant and it's very expensive. And the index of refraction of a diamond is very high. And so what that means is the critical angle is very large. So if you have some white light coming in the top of your diamond, it passes through, and down here it's totally internally reflected. None of the light can get out. So it bounces over here. When it reaches here, it's totally internally reflected, and so it bounces this way, and then it pops out the top. Violet light also goes in there, bounces around, and comes out the top, and it even gets a little bit of dispersion when it comes out the top. So if you look really carefully at a diamond, you'll see there's actually little places where you can kind of see kind of different patches of color. That's because of the dispersion. But you could say, well, why don't you just make a mirror, right? If this was mirrored, then all the light that hit the top would bounce back, and it would also be shiny, right? Well, a diamond is actually even more shiny than a mirror, because even light that comes in the bottom, so light that comes in from the side here, will be internally reflected and pop out the top. So diamonds are actually extra brilliant. Not only does all the light that hits the top bounce back at you, but all the light that comes in from the sides and the bottom also comes out the top and makes it extra brilliant. So diamonds are typically mounted with little tiny prongs that hold the diamond on so that lots of light can get underneath. And it's the light underneath that gets internally reflected and pops out the top that causes a diamond to be so brilliant. So that's another example of total internal reflection. So today we learned about dispersion, the spreading out of light colors because of the slightly different index of refraction, and we learned about total internal reflection. Because of the constraints of e-learning, we are not going to solve problems with total internal reflection, so your assignment is just to solve a couple of problems that involve dispersion.